Hello everyone. So in this video we will be studying about another reason why do we require synchronization. We have studied what is synchronization, what are the methods, how this synchronization can be used. So in this video we will be studying another requirement of synchronization, that is deadlocks. So deadlock is the reason where we require the synchronization. Let us understand what is a deadlock, when it happens, what are its necessary conditions that a deadlock will occur. So first in this we will study about the system model. System model in the sense, what does a system have in itself, what it gives to the other processes. So when one system is running, there will be many processes running into it. So and these processes will require the resources which are present with the system. These resources will be shared with all the processes which are present in the system. So resources in the sense, they may be physical resources or it may be the logical resources. Physical resources in the sense, we are having now printers, we will be having some memory. So these are the physical resources. And logical resources means files, whatever memory space we are having, so that is a logical resource. Some data which is shared between the files, this is a logical resource. So these resources have to be shared between the processes. When sharing comes into picture, we have to keep into mind that one process is waiting for some data which is taken by other process. So in such situation, waiting becomes more longer. So this longer period of waiting may sometimes leads to deadlock. Okay. So what is that? We will see now. So if this system will be having many resources, these resources will be shared by the processes, and one concept here is about many instances of resources. What do you mean by instances? Means number of resources. Now for example, when two printers are connected to a system, so it is said that there are two instances of that printer. Means total number of resources of same kind. If it is a multiprocessor means many processors. Suppose if there are 2 or 3 processors, it is said that there are 3 instances of the processor. Means the number of same kind of resources are called as the instances, and these instances will be given to the processes. So that is what available resources which are present with the system, they can be shared. Then we will be studying what are the steps to acquire these resources. What are the steps this processor will follow to acquire the resources? It mainly will follow the 3 steps. That is request. First it will request the resource by some system call. So in the previous module we have seen different types of system call. So for request is one of the system call, release is one of the system call. So such type of system calls will be used for acquiring the resources. Once it requests the resource, if the resource is available, it will be given to that process. If at all the resource is not available, then that process will be kept under waiting queue. Okay. Then after that what will do? Once a process is allocated with a resource, then it will use that resource. What task it want to do with that resource, that will be done. After finishing the task, when that resource is no more required, that time that resource will be released. This releasing, requesting and using the resources of a system will be done using the system calls. This is not, they will be done using the different types of system calls. Then there will be many resources. We have to keep some information about what resources are available or how many instances are acquired, how many instances are free. For that purpose, there is something called as a system table. What this system table is consisting? It will be consisting of the information regarding the availability of the resources. Whether these resources are having how many instances, how many are free, how many are acquired by whom, when it will be released. Like this, all these information will be present in this system table. These data can be accessed by the operating system to allocate the resources to the processes. Then This is a basic information about the system. Now coming to the concept of deadlock. When this deadlock is told to happen. When it will happen is, see for example directly I will give you the example here. A system is having a 3 CD drives. Okay, process P1, P2 and P3. All of them are using one of the drives. Okay, then but they are not finishing the task with one drive itself. They want some another drive now, which is required by which is taken by P2. P1 wants a drive which is taken by P2. P2 wants a drive which is taken by P3. P3 wants a drive which is taken by P1. Each one of them are having one drive and waiting for another drive which are acquired by others. But they also are waiting for the other drive. In such situation, waiting periods becomes long. When it becomes long, it goes to an extent that it will not come out of that, means those processes will not be terminated. Means they keep on waiting. They will not never complete their task. So such situation is called as a deadlock. A set of processes are said to be in deadlock. A set of processes are said to be in deadlock when one processes are waiting for the resources which are acquired by another processes. So this is indefinite waiting. This is called as a deadlock. So this is what happens when you are not managing or writing the programs which will avoid such conditions. So after this we will be seeing with the deadlock characterization. About the deadlock characterization, means what are the necessary conditions when a deadlock will happen. That is what is deadlock characterization. So when what are the necessary conditions? So these are the 4 necessary conditions which should be present. All these 4 should be present, then only a deadlock is said to occur. So first one is the mutual exclusion. So what is mutual exclusion? As we have seen in the synchronization module, when one process is in its critical section, or when one process is using a shared resource, other processes should not be allowed to use that shared resource. This is mutual exclusion. But when you are violating this mutual exclusion, there is a possibility that deadlock will occur. Okay. So when there is some unshared variable, or when there is one unshared resource, when some another process makes the request for using that unshared resource, that time that process should be kept in waiting queue. Okay. So this should happen. But when this is violated, that time a deadlock is said to occur. So the next one is the hold and wait. What do you mean by hold and wait is, see one process is holding some resource. See, it is for executing completely, a process may require many number of resources. So out of these many number of resources, it will acquire one resource. Means it is holding one resource and it is waiting for other all resources. So these other all resources are used by some other processes. That time also deadlock is said to occur when mutual exclusion and hold and wait. Next is no preemption. When there is no preemption also, the deadlock will occur. What do you mean by no preemption? Means once the process starts executing, it is not stopped. It is not suspended in between. It is not halted. So that is called as no preemption. So what is the result of this one? When there is no preempting, then that resource is held by that process until it completes its execution. Is it not? So that time the resource is not released. If this resource is not released, it cannot be used by the other processes. Other processes keep on waiting. Since the waiting period becomes long, deadlock is happening. So when there is no preemption used, that time also deadlock is said to occur. Last one is the circular wait. Circular means what? second is waiting for third, third is waiting for fourth. Similarly, last one is waiting for the resource which is occupied by the first one. So this is called as a circular wait. So in this condition also deadlock is guaranteed told to occur. Okay, these are the four necessary conditions for deadlock to happen: mutual exclusion, hold and wait, no preemption, and the last one is this circular wait. So these are the necessary conditions. So when deadlock is said to happen. Next we will be seeing graph which will tell you about the how to represent the resources, instances of resources, processes, which processes are acquiring the resources. So in this graph is called as system resource allocation graph. In this system resource allocation graph, processes are represented by the circles. Inside the circles we are writing the process numbers. Okay, we can say that as a process IDs also. Then resources are represented by a rectangular box. Resources are represented by a rectangular box. Also, the instances of resources means say many number of same type. They are indicated as the dots inside that rectangular boxes. Now you can see here P1, P2, P3. These are the processes which are represented using the circles. These R1, R2, R3 and R4. These are the resources. The dot inside these, it means the instances of this resource. There are 3 instances of resource R4, then 1 instance of R2. Instance means what? How many number of same type of resources are present with the system. So like this we are representing. Now coming to the, I told you it is a graph. So a graph means it is a collection of vertices and edges. What are these vertices here? These itself processes are the vertices. What about the edges now? There are 2 kinds of edges here. One is request edge, another is the assignment edge. What is request edge? When one process requests some instance of resource, so now there will be an edge from the resource, now there will be an edge from the process to the resource. From the process to the resource. Here, from the process to the resource. So this edge is called as an request edge. From process to resource. That is what I have mentioned here. Process PI is requesting another resource RI. So this is called as an request edge. Then another thing here. If a resource available is allocated to a process, then there will be an edge from the resource instance to the process. From the resource instance to the process. From RI to PI. From the resource instance to the process. This is called as assignment edge. So collection of these vertices and the edges will give you the system resource allocation graph. What are the sets used here in this graph? So the sets used are P, R and E. What does P means? P means the processes. So now in this graph, whatever graph we are having, how many processes are there? 3. So P1, P2, P3. This is a set for P. What about the resources? We are having 1, 2, 3, 4. R1, R2, R3 and R4 resources we are having. What about the edges? Now you can see here P1 to R1. This is which type of edge? From the process to the resource. So it is, yes, it is a request edge. Then we are having from P2 to R2. Again a request edge. Next from R1 to P2. So from the resource instance to the process, it is an assignment edge. So I have written here edges. So these are the 3 sets for this particular graph. Then what are these resource instances used here? Resource instances are, there is only one resource instance of resource R1 and R2 as well. Then there are 2 instances of resource R2. There are 3 instances of resource R4. What about the process states? What are the process states? See, process P1. Process P1 has requested for an instance of R1 while it is holding one instance. It is already having one instance of process P1 here. deadlock is there or not. Using this resource allocation graph also, we can find out whether there is a deadlock or not. How you can find out? If there is a cycle existing in this graph, it will become a necessary condition. If there is a cycle existing in the resource allocation graph, then it will become a necessary condition that a deadlock may happen. Please mind, I am saying may happen. So necessary means what? If this is a necessary requirement is there, but it is not a sufficient condition. Okay, it is not a sufficient. If there is a cycle, then it is only the necessary condition. Okay, then how to find out the deadlock here? If and only if there are only single instances of the resources. If there is single instance of each resource, and then there is a cycle existing in the resource allocation graph, then that cycle will become necessary and sufficient condition for the deadlock to happen. If there are only one instances, then deadlock will happen in such cases if there is cycle existing. Please note the difference between necessary and sufficient. See, necessary is one of the factor where deadlock can happen. Sufficient condition means if there is only one instance and there is a cycle, then it is sufficient that a cycle is present for deadlock to happen. Let us see one example here. See, in this there is a cycle. See, there is a cycle from P1 to R1, then P2, then R2, then here P1 R1, this one. So it is having a cycle. So let us see the clear example here. Now P1, so what about this graph? P1 is, see, this is R1, R2, and let me take this as resource R3. See here, in this one P1 is requesting for the resource R1. That resource R1 is present with P2. So P2 will be waiting, P1 will be waiting for the resource which is present with P2. What about P2? P2 is having the resource R1, but it is waiting for the resource which is taken by P3. What about P3? P3 is waiting for the resource of R2 which is taken by P1, and it is having the resource R3 which is required by P2. Now you can see a cycle here. See, this is a cycle which is present here. Is it not? There are only one instances here. So now cycle is necessary and sufficient condition in this situation. So when these two will release, see, when P1 and P2 will release the resources, that time P3 can execute completely, or P1 and P2 are waiting for this resource which is taken by P3. So here this will become a necessary and sufficient condition. The cycle which is present in this graph will become a necessary and sufficient condition for a deadlock to happen. Let us see another example. In this example, there is a cycle, but it does not cause the deadlock. Let us see how. See here, P1 is requesting for the instance of this one, R1, that is taken by P2, another instance is taken by P3. Then this P4 is requesting here. P4 is having an instance of R2, and this instance is given to P1. See, P1 will release. If P4 will release this resource, this instance will become free. When this instance will become free, this resource allocation can be done to P3. P3 will complete its work. Is it not? Like that. So here cycle is present, but it is not a sufficient condition. Because if one process is releasing the instance of the resource, then deadlock will not happen. Is it not? That is why in some cases you have to handle it carefully. You have to see whether the cycle here present is a necessary and sufficient, or it is only necessary condition for a deadlock to happen. Then in this graph, see, this is a graph which actually is. Suppose one instance is released, then what will happen? Its request edge will be removed. When one instance of a resource is released, then that assignment edge and the request edge available. So like that you can draw these graph of resource allocation. Then what are the different methods of handling? These are the actual basic methods or some abstract idea given for handling the deadlocks. First one is use a proper protocol for avoiding these deadlocks. Proper protocol means some set of rules and regulations. So when you are writing the programs for the processes execution, you must keep in mind that deadlock should not happen. In such cases, you are going to write the strict rules so that synchronization is maintained. Deadlock is not occurring. Next one is, if at all deadlock happens, see, human beings while writing the programs are tend to do some errors. So if at all a deadlock is happening, you have to detect the deadlock and you should write the programs to recover from those deadlocks. So this is the second method in which you are handling the deadlocks. Next one is ignore the deadlocks. So let the deadlocks happen, let it do anything, let it not come out of that deadlock situation. System is not bothering. So this is the most what you can say, irresponsible method you can say. So if deadlock is happening, what will happen to the performance of the system? Since the processes are not executing, the performance or the efficiency of the system becomes less, is it not? So this third method is not useful one. So we have to develop the protocols and the method for the two methods which we have seen here, using the proper protocols, and if at all deadlock happens after using these proper protocols also, there should be some methods, there should be some ways of detecting it that deadlock has happened